I think we can start now if you're ready, sir.
Ready.
Okay, so hello and welcome everybody to today's lecture. Today we have with us Professor Jim Fuller, who is a professor at Caltech. He works in a wide variety of research topics, mainly in theoretical astrophysics, including topics such as white dwarf mergers, black hole spin, neutron spin, and many more. So today we're lucky to have with us Professor Jim Fuller, who is going to be talking about gravitational waves.
Okay, thank you. Thank you for coming, everybody. I realize it's very late at night there, so I guess you're getting some training on how to be a good observer by staying up late to do your astrophysics. I appreciate you coming. I'm just going to share my screen and start my slideshow. Okay, does everybody see my screen?
Yes, sir, we can see your screen.
Okay, so I work on many different topics in theoretical astrophysics. They're broadly focused on stellar astrophysics and related topics. So today I'm going to tell you about a couple interesting consequences of gravity waves, which are different from gravitational waves. There can be a lot of confusion. These are waves that propagate in stably stratified regions of stars or planets. They're basically buoyancy waves. So what's shown here is a simulation of gravity waves in the radiative interior of the sun. So you see the convection around the outside, and inside you have gravity waves that are excited by convection. And gravity waves have many consequences, so I will talk about results that relate from exoplanets all the way to black holes. But a lot of it is just due to the fluid mechanics that's happening inside of stars or planets as they evolve. So like I said, gravity waves are these low-frequency buoyancy waves that propagate in stably stratified regions of stars. So here's another simulation, this time by Andrea Cristini, of carbon shell burning in a massive star. So here's a convective burning shell. But above this shell, you see these other motions that are largely horizontal. These are gravity waves. And then it's a little harder to see, but you also see some waves down here that are also gravity waves. And those are waves that are excited by the convective motions. They propagate away from the convective shell, and they carry energy and angular momentum. So they can have really important consequences. In addition to carrying information, energy and angular momentum, they carry information. So they allow us to do a lot of interesting asteroseismology, which I'll discuss. But also gravity waves are just about everywhere from planets to galaxy clusters. The waves can have an important effect on the medium that they propagate in. So there's lots of fun topics. The first topic I'm going to explore is tidal effects in binary stars and planet systems. This is a case where we can directly see gravity waves, and so we can really see their consequences firsthand. And I've worked on this topic with many different observers who have helped collect some of the data I'm going to show. So I'm going to start with a type of binary star called a heartbeat star. What these are binary stars in very high eccentricity orbits. So I'm going to play a little movie. This is just a heuristic demonstration of what a heartbeat star is. So you have two stars that are in a very eccentric orbit, and every time they pass through periastron, they get very close to each other. And so the tidal force of each star excites pulsations in the other star. And so the stars keep pulsating throughout their orbit. And so if you measure the luminosity of one of these systems, that's what's shown in this bottom panel here, the luminosity is always fluctuating up and down due to the tidally excited gravity. In this case, there are gravity modes that are excited inside of the star. So you also get a big spike near periastron. That's due to basically the sort of bulk distortion of the star, but you also get the continual pulsations that are produced by tidally excited gravity waves. And in this case, those gravity waves form standing oscillations inside of the star called gravity modes. So here's another example of, this is real data, Kepler data for one of these heartbeat star systems. And it's been phased on the orbital period. So you see the same exact pattern repeats every orbital period of this star. So you see this oscillation here that continues throughout the orbit. That's a tidally excited gravity mode. The amplitude is about 1 part per thousand or a little less. So these are very difficult to see unless you have nice space-based photometry. And in addition, every time the star goes through periastron, there's a bigger variation here caused by the tidal distortion of the star. That's often called the equilibrium tide. So we see both of these effects at the same time, but we can get a lot of information about the evolution of these systems by understanding the tidally excited oscillations, these gravity modes that we see here. So if you take a Fourier transform of this light curve, you see two main effects. You see a series of peaks that occur at every integer multiple of the orbital frequency. You see these peaks at integer multiples because you get the same pattern of the light curve. It repeats every orbital period. So that means everything you see in the light curve, or almost everything, occurs at an integer multiple of the orbital frequency. So all these peaks down here, these are mainly caused by this big distortion here that occurs near periastron. That kind of looks like an EKG diagram or a heart monitor, so that's why these are called heartbeat stars. But you also see this oscillation here corresponds to this big peak in the power spectrum here. And that's due to one of these tidally excited gravity modes in one of the stars. So we can learn a lot from the amplitude of this oscillation and from its frequency. In this case, it happens to have a frequency of exactly 26 times the orbital frequency. But those modes can appear at many different multiples of the orbital frequency. And there's a big diversity in these heartbeat stars. So these are all light curves of different heartbeat stars. So they can look very different depending on their inclination and their eccentricity, and whether or not they have tidally excited gravity modes. So one of the most interesting stars that we've come across is this one. This is the light curve of a star called KIC 8164262. And what you see here, all this, what looks like noise right here, this is actually a tidally excited oscillation. And this distortion right here, this is the distortion that happens right at periastron, where the two stars are closest to each other. So what I'm going to do is I'm going to zoom in on this section surrounding periastron. And what you see is you see this tidally excited oscillation here, which has a very steady amplitude, and then you see the big dip and rise at periastron due to the equilibrium tide. So in this case, this oscillation here has a very large amplitude, which is still only 1 part per thousand, but as far as heartbeat stars go, that's pretty extreme. And it has an extreme frequency. It occurs at exactly 229 times the orbital frequency. So it's a very high multiple of the orbital frequency, and that occurs because this particular system has a very high eccentricity. So if you take a Fourier transform of the light curve of this system, what you see is you see this enormous peak right here that's at the 229th harmonic that's caused by this tidally excited gravity mode right here. And everything else is really, really tiny in amplitude relative to that one peak. So that's a little unusual that you would have one oscillation that's so much larger than any other oscillation in the system. And that's giving us a clue that something interesting is happening in this case. So what I've done is work on modeling the amplitudes and frequencies of these oscillations. And for the most part, you can calculate what to expect. So we know that the luminosity fluctuations produced by tidally excited oscillations they just occur at some amplitude and at some orbital harmonic. So in other words, some multiple n of the orbital frequency. And then there's some phase offset as well relative to periastron. So we can predict what we expect these amplitudes to be. These are basically just the amplitude of a forced harmonic oscillator. So that's what this equation is telling you here. There's a bunch of terms here that are the strength of the tidal forcing, the visibility of the mode, the spatial and temporal overlap between the forcing and the mode. But what's really important here in this equation is this last factor, which is the resonant detuning factor. You can see it has a Lorentzian form. That's what you get whenever you have a forced harmonic oscillator. So all of these prefactors can be calculated fairly accurately as long as we have a good model of the system. But this resonant detuning factor, you can't really calculate exactly because it depends on the difference between the oscillation mode frequency of the star, which is omega alpha, and the tidal forcing frequencies, which just occur at integer multiples of the orbital frequency. And basically, we can't model the stars accurately enough to reliably predict these difference frequencies because these can be very small numbers. So even tiny changes in the stellar model will change what this number is. And the damping rate of these modes is usually very small. So basically, this number in the denominator can be very small depending on the exact model of your star. So when you have a mode frequency that's equal to a forcing frequency, that means it's resonantly excited. And that means this denominator is close to zero. And so you have a really large amplitude of your tidally excited oscillation. So we expect some near resonances, but it's hard to predict exactly which modes they should occur for. So you can estimate this factor statistically. How many resonances do you expect to see in a given system? So that's what I've done, and that's what this plot shows. The blue line is a prediction for how many modes you should see as a function of amplitude. So you should see many low amplitude modes, very few high amplitude modes. What you see is that this very large amplitude mode in this system, we only expect to see that in 1 out of 30 or so of these systems. So it's very unlikely we should see such a large amplitude mode in this system just based on pure chance. So that suggests that this mode that's resonantly excited here is not being excited by pure chance, that there's actually some more interesting physics going on. So I believe what's happening in many of these systems is a process called resonance locking. And so here's the idea behind that. This results from feedback between the orbits and the evolution of the stars themselves. So what I've plotted here is the tidal migration time, or you could think of it as similar to a tidal circularization time, as a function of semi-major axis or orbital frequency of the system. So right here in the middle of this plot, this would correspond to a resonance between one of the star's oscillation modes and the orbital forcing. So right at that resonance, you get a really large amplitude oscillation mode. That means you get a lot of energy dissipation. And that means that the system will circularize very quickly. And so that will cause the semi-major axis to decrease. And so what that means is this tidal migration time is very short, right near resonance. And there's some point at the side of the resonance where the orbit basically decays at the same rate, at the exact rate required in order to keep the mode in resonance. Because what happens in these stars is they evolve slowly. So their mode frequencies change slowly. In most stars, their gravity mode frequencies slowly increase with time, on a stellar evolution timescale of a few billion years. And so there's some point near the side of this resonance where the orbital frequency decreases at the exact right rate to keep the mode in resonance, such that basically the system stays on the side of this resonance. And so in other words, the semi-major axis decreases at the exact right rate so that the orbital forcing frequency remains resonant with the oscillation mode frequency of the star. And this is a stable fixed point because imagine we have the system right here so that this fixed point is moving inwards at the same rate as the resonance. If we were to perturb the system inwards, then the tidal dissipation rate would decrease, and so the resonance would catch back up to the system, and it would sort of sweep it along. If we perturb the system inwards, the tidal migration rate would increase, and so the system would migrate back to this stable fixed point. So I'll give another demonstration of that idea in a bit, but the point is, if the system is in this state, we can predict the amplitude of the tidally excited oscillation, and so we can predict what the observed amplitude of an oscillation mode should be if it's in this state. So that's just given by this equation here. So I've created some models for that system and predicted the amplitudes of resonantly locked oscillations. That's what's shown in this plot. This is amplitude as a function of orbital or mode frequency, I should say. And the big oscillation we see in the system is this pink star. And the green circles are the expected amplitudes due to resonance locking. And you can see that they're pretty close, especially for m=1 oscillation modes of the star. They're pretty close to what we expect to see. So this is good evidence that this mode is indeed a resonantly locked oscillation mode. And this is, I think, some of the first real observational confirmation that this process is occurring in these systems. All these other points down here, these are smaller amplitude modes that aren't resonantly locked. They're just sort of excited to lower amplitudes by chance. So we think resonance locking is happening in those heartbeat star systems. So there are a few other examples in astronomy where we think a resonance locking process may also be operating. So now I'm going to switch and talk about how this process can affect planetary systems. So one place where this could be very important is actually in our own solar system, especially in the moon systems of giant planets. So in the Saturn system, as an example, Saturn is orbited by many moons, the most massive of which are these inner moons, Mimas, Enceladus, Tethys, Dione, Rhea, and then Saturn's most massive moon, Titan, is a bit further away and is not shown on this plot. But in this case, just like our own Earth's moon, these moons are migrating away from the planet. They're getting pushed outwards because the planet spins faster than the moon's orbit. And so that means the tidal effects cause the moons to gain angular momentum and move away from the planet. And what's really nice about our own solar system is that we can actually measure the migration rates of these moons. It's very challenging, but we can do it through long-term observations of their positions. So I will come to some of those results in a second. I'm going to skip through some of this. The point I want to make is that we don't totally understand which energy dissipation mechanisms are at work in giant planets that drives the migration rates of their moons. So there are several ideas out there. One of them is the idea that inertial waves, which is a different kind of wave that propagates in convective regions of planets. One idea is that those inertial waves are tidally excited and then damp out energy, and that causes the migration of the moons. So this is a calculation of the energy dissipation rate created by inertial waves as a function of forcing frequency. This is done by Ogilvy and Lin about 17 years ago. And you notice this is a log scale. So what you get is there are certain frequencies where you get much stronger energy dissipation than at other frequencies. And you can think of these frequencies as being resonances with oscillation modes. in this case, inertial wave oscillations of the planet. They're formally not oscillation modes, but what's important is that there's this structure where at certain frequencies you get a lot of dissipation, and at other frequencies very nearby you get very little dissipation. And just like with the modes of stars, the exact frequencies of these resonant peaks, they change with time because the planets evolve. So we might expect these frequencies to change on a time scale of billions of years or so, the time scale at which the planet structure is evolving. So in the case of giant planet systems, if you zoomed in on one of those resonances, so this is a very similar plot to what I showed you before, you might see a tidal migration time scale, which is this blue line, that's a function of semi-major axis, that has a very narrow peak surrounding one of these oscillation modes. And the location of this resonance will either move inwards or outwards, depending on how the planet is evolving. In this case, the moons are migrating outwards. So if you have any of these resonant peaks where the resonance location is also migrating outwards, then you can have resonance locking. Then there's a point on the side of this resonance where this blue line intersects this green line. And that means this resonance location is a moon at this resonance would migrate outwards at the exact same rate as this resonance location, such that it stays at this exact same point on the side of the resonance. So you can think of a moon in a resonance lock as surfing a wave. So there's some point on the side of a wave where the wave is pushing you forward basically at the same rate that the wave propagates. And that's the basic idea behind resonance locking, is that the moon finds some place on the side of one of these resonances where it migrates outwards at the exact same rate that the resonance is moving outwards. And that's a very natural place to find a moon because it's a stable equilibrium. And even if the moon wasn't migrating at first, as long as some of these resonant peaks migrate outwards, they will sweep up the moons and push them inwards. Just like a wave at the beach sweeps up debris on the surface and pushes surfers and driftwood and seaweed and all kinds of other things inwards. So that's the idea. And if this is happening, then what this means is that the migration rate of a moon is basically just directly linked to this time scale T alpha, which is the time scale on which the mode frequency is evolving due to the structural evolution of the planet. So there can be two effects, either the structural evolution or the spin evolution of the planet. So they might both contribute. For inertial waves, it turns out we expect this to reduce to a tidal migration timescale that goes roughly as just the spin frequency evolution timescale of the planet. And that's because inertial wave frequencies are related to spin frequencies of the planet. So we expect this tidal migration timescale basically just to be very similar to the planet's evolution timescale. People often like to discuss tides in terms of a tidal Q, or a tidal quality factor. So you can translate this tidal migration timescale into an effective quality factor, and that's given by this big ugly equation. But the point is, we don't expect this number to be constant. What we expect to be roughly constant is this tidal migration timescale. In other words, that should be almost the same for different moons, and it should be almost the same as a function of time within the system. So we might expect all the moons to be migrating out at roughly the same time scale. So we can compare this with the data. And this has been a heroic effort by Valerie Linné and Paolo Tortora's group in Italy, where Valerie Linné has used long-term astrometric measurements of the moon's positions, and Paolo Tortora's group has used Cassini measurements of Titan's position in order to pinpoint the location of the moons and therefore determine whether or not their orbital frequency is increasing or decreasing with time. What they find is indeed the orbital frequency slowly is decreasing due to the migration of the moons outwards away from the planet. So what they do is they can equate that with an effective tidal quality factor of Saturn that's driving the outward migration of the moons. So they've managed to make these measurements for Mimas, Enceladus, Tethys, Dione, and Rhea. That's what's shown by these pink points. And the effective tidal quality factor that they're getting, what you can see is it's very different for different moons. So for Mimas, it's very large. For Rhea, it's very small. It's a tidal quality factor of only a few hundred. And this is already a couple orders of magnitude smaller than what has been proposed in the literature as the minimum possible value of Saturn's Q, assuming that the moons formed at the same time as Saturn and migrated outwards to their current positions. Those kinds of constant Q models predict that Saturn's Q should be up here of order 10 to the 4, 10 to the 5. So clearly, Rhea is migrating much faster. In other words, Saturn has a much smaller tidal Q that's driving Rhea's outward migration. And the most shocking development in this picture is for Titan. So previously we didn't have any measurements for Titan, but using the astrometric and Cassini data, these groups were able to measure a migration rate for Titan, Saturn's largest moon. And because Titan has such a large semi-major axis, most people expected it wouldn't be migrating. But if you look at the data, it actually looks like Titan is migrating, and the effective quality factor of Saturn that's driving that migration is incredibly slow. It is incredibly low. It's of order 100. So this is actually similar to the tidal quality factor of Earth, which is remarkably low compared to what people thought. So the red data is the Cassini data, the purple data is the astrometric Earth-based data, and you can see that they agree. And they also overlap with these blue points, which is the expected tidal quality factor, assuming that these moons are driven outwards by this resonance locking process with inertial waves. So a better way of seeing that is if you predict the tidal migration timescale, then like I said, the theory predicts that the migration timescales of all the moons should be roughly the same. So in this very simple model shown here, they're all exactly the same at 9 gigayears. We don't expect them to be exactly the same, but we expect them to be, within an order of magnitude or less of the same timescale. And indeed, that's what you see. So the purple points are the measured tidal migration timescales. And you can see that they're all of order 10 gigayears, or within a factor of 2 of 10 gigayears. So this, I think, is very convincing evidence that this resonance locking process is happening inside of Saturn, and that is driving the outward migration of its moons. So that has a lot of implications for the history of the Saturn system, for things like tidal heating of the moons, for the formation of the moons. So I won't get into that right now. I have a couple slides I can come back to if people are interested. But the last thing I wanted to say is that this process could potentially operate in many other situations. So it may operate in exoplanet systems, and that's one of the things I'm working on with the student, Lin Hao Ma. We actually just submitted this paper yesterday, so these are preliminary results, so they may change. But what's plotted here is very similar to the plots you've already seen, but now for a model of an exoplanet system around a sun-like star. We're looking at short orbital periods where tidal effects are important. And we see many exoplanet systems at these very short orbital periods. So what's plotted here is the blue line is a calculation of that inward tidal migration rate. So in this case, exoplanets tend to have their orbits decay. They migrate inwards until they're swallowed by the host star. And this blue line is a calculation of the inward migration rate of an exoplanet. And you can see it has a very small value centered around a resonance. In this case, it's a resonance with one of the star's oscillation modes, one of its gravity modes. The orange line is a slightly different model accounting for nonlinear damping, which is a bit harder to calculate. So this is only an approximation, and it changes the shape of this resonance. But the important point is that there's some point on the side of this resonance, either here in the linear model or here in the nonlinear model, at which the inward migration rate is the same rate at which the resonance location is migrating inwards. So right here, you could have a planet get caught in a resonance lock and migrate inwards at the same rate that the gravity mode frequency increases. And when that process happens, that's actually very convenient for theorists because we know how to calculate the structure of a star like the sun. We can calculate quite accurately how fast these gravity mode frequencies increase. And so if resonance locking occurs, we can calculate quite accurately how fast a planet's orbit should decay. So let me show you an example of that. What's shown here is a plot of the orbital frequency of an exoplanet, which is this red line, along with the corresponding gravity mode frequencies, which are these black lines, for a model of a sun-like star. So what I'm going to do is, if you zoom in right here, what would happen in a system like this is you would start with a planet. At first, it would be far away from resonance, so it wouldn't be migrating. But as the system evolves, the planet would come into resonance with one of the oscillation modes, which is, in this case, is this black line here. And then it will become resonantly locked with the oscillation mode. And so it will basically move in lockstep with one of these resonant locations. And so if we zoom back out, the planet would be in resonance with the same oscillation mode, potentially for gigayears. And so its orbital frequency would steadily increase at a rate that is easy to calculate. So that's what we think is happening in some of these exoplanet systems. And so in that case, we can calculate the orbital period evolution of a system. So that's what's shown in this plot. I want to focus on this red line, which is the orbital evolution of say a typical super Earth or mini Neptune system. In this case, it's started at an orbital period of a few days. And if resonance locking occurs, then we expect it to follow this red line. In other words, its orbital period will slowly decrease on a time scale of several gigayears, which is basically the evolution time scale of a star like the sun. So in this case, you get this steady orbital decay. You can translate that to a tidal quality factor, which is how people often parameterize these effects. And early in the evolution of this system, this corresponds to a very low tidal quality factor, a number of something like a few times 10 to the 4. So in other words, according to these models, this planet is actually migrating much faster here than people would have predicted based on parameterized models that they've used in the past. Usually people assume the tidal quality factor is something like 10 to the 6. And so that would give you an orbital migration rate that's, 1 or 2 orders of magnitude too slow. But as the planet gets closer, what happens in these models is you can see that the migration time scale is roughly constant, but the effective tidal quality factor is increasing enormously. So in other words, what this means is when the planet's at very short orbital periods up here, this corresponds to a very large quality factor, which actually means much slower migration than people would have predicted in the past. So clearly the history of these systems might be very different from how people have modeled them in the past. And we still have more work to do to make more detailed predictions, but we think that's what's going on. The last thing I want to say on this topic is that if you do a similar model for a hot Jupiter, so this blue line is a one Jupiter mass planet, the green line is a 5 Jupiter mass planet. For these kinds of planets, we actually don't expect this resonance locking process to occur. And the reason is that nonlinear effects are probably very important. So there's been some nice work by Nevin Weinberg, who's shown that basically the nonlinear effects prevent these resonances from existing when you have a very massive planet that's forcing the tidally excited oscillations. And so in that case, you don't get resonance locking, you just get a process of continuous wave excitation and wave dissipation inside of the star. So that gives you a very different kind of path in this diagram, a very different model for tidal energy dissipation. And that corresponds to these tidal quality factors shown in these dashed lines here. So you can have very different histories depending on the mass of your planet and potentially on the type of star involved as well. So we will continue to make predictions for those exoplanet systems. So I wanted to stop and pause here before I go on to the next part of the talk. Are there any questions on this part?
So we usually keep the questions to the end.
Okay.
If that's okay with you, sir.
Yep, that's fine. So I will move on to the next subject, which is the spin of the interiors of stars, which is also related to things like gravity waves and fluid dynamics of the interiors of stars. And I think one of the really exciting implications of this subject is that this determines the spins of neutron stars and black holes. It potentially determines the luminosity of supernovae that occur at the end of massive stars' lives. And the reason is that if you take a star and let it evolve, typically what happens is as the star evolves, the core contracts. And if it conserves angular momentum, the core will start spinning faster and faster. The envelope tends to expand, and so if it conserves angular momentum, it should spin slower and slower. So the star naturally develops a lot of shear where it has an envelope. And what we don't understand very well is how much friction occurs between the inner layers and outer layers that causes the core of the star to spin down and the envelope of the star to spin up. So that's called angular momentum transport, and that's a topic that I have worked on a lot. And it has really been helped by the fact that we're now getting asteroseismic data that actually gives us direct measurements of the rotation rates inside of stars. So I'll go through this fairly quickly since I'm running a little low on time. But the basic idea is if you just measure the pulsations of a star, in this case, this is the Fourier transform of the light curve of a pulsating red giant star. What you see is that the dipole oscillations, so these are the spherical harmonic index L=1 modes, they're split into triplets. You see these three different peaks here. It's split into a triplet by the rotation of the star. So this is basically an oscillation mode that's propagating with the rotation of the star. So it's shifted to higher frequency. This is a mode that's propagating counter to the rotation of the star. So it's shifted to lower frequency. And what you can see, so basically if you measure this frequency splitting, you can measure the rotation rate of the star. But it turns out this is basically a weighted average of the rotation rate of different layers of the star. So you see the rotational splitting here. You can also see it for this mode here, and what you see for this mode is that the splitting is much larger, right? We have much wider separations here than we do here. And the reason is that this mode spends most of its time propagating in the core of the star, whereas this mode propagates near the surface of the star. And what this tells us is that the rotation rate of the inside of the star is actually faster than the rotation rate of the outside of the star. So you can see this directly in the data. And if you model this, you can figure out that the cores of these stars are often rotating maybe 10 times faster than their surfaces, something like that. So Benoit Moser's group has compiled measurements of the core rotation period for many stars So here are several stars on the red giant branch. Here are several stars doing helium burning in the core that are on the clump. And you can see these core rotation periods are typically 10 or 20 days on the red giant branch, something like 100 days on the clump. And you compare those internal rotation rates with models. And what you find is that the models, basically none of them matched the data before this data was taken. So the data here, this is a plot of rotation period of the core as a function of basically radius of the star. So stars migrate from left to right on this plot as they evolve. And these black lines are different models for how angular momentum is transported in the star. So if the star was rigidly rotating as a solid object, then as it expands, it should rotate much slower. And that would predict a rotation period that's quite a bit longer than what we actually see in the cores of these stars. So clearly this isn't happening. If you assume that no angular momentum is transported within the star, such that the core just contracts and spins up and conserves its angular momentum, then it would be rotating at a rate that's more than 100 times faster than these measurements. So clearly there is a lot of angular momentum transport in the star. And prior to this, the most popular model was probably this red line, which is called the Tayler Sproit dynamo. This is a model for how magnetic torques can redistribute angular momentum within the star. And this model does better, but it's still predicting rotation periods that are about 10 times faster than what's observed. So clearly this model isn't working very well either. So what I've done is look at some of the physics of this Tayler Sproit dynamo. So what happens in this model is you start with a very weak magnetic field in the star, and as soon as you have any differential rotation in the star, then what happens is the differential rotation tends to wind up the star, the magnetic field, like a spring. And eventually the spring gets wound up tight enough that it becomes unstable and slips sideways. This is a kink instability that's well known in things like tokamak reactors, where a predominantly toroidal magnetic field slips sideways. That's called the Tayler instability in this case. And what that can do is the slippage can basically regenerate the radial component of the magnetic field through a dynamo process. And so you have a torque, BR, B phi, roughly, that's basically exerting a torque that transports angular momentum between the inner and outer layers of the star. So we don't understand the saturation of this instability very well, so it's hard to actually predict that torque. So what I've done is sort of make some arguments that are different from the original picture advanced. And mostly, I think what's unclear is how the nonlinear damping saturates this instability and prevents the fields from being amplified further. So I won't go into these details, but basically we think that the instability, the damping rate is actually a little smaller than originally proposed. What this means is that the magnetic field amplitudes can grow to larger values, so you can get larger torques than originally proposed. And so the original proposition for how these torques scaled with rotation rate divided by the Brunt-Beisolo frequency, which is a measure of stratification in the core of the star. So originally it was proposed these scale roughly as the fourth power of this number, and this is a very small number in stars. In our modified picture, it scales as the second power of that number. So that means there's a lot more angular momentum transport in this updated model. And we can put that into models of stars and predict their rotational period evolution, and that's what's shown by this red line. So this is a model of the core rotation period as a function of time after the main sequence for a star on the red giant branch. And what you can see is these core rotation periods in this updated model, they're something like 10 or 20 days, which is pretty similar to what we see in the data. On the clump, it's the core rotation period of about 100 days, which again is pretty similar. And when the star contracts into a white dwarf, the star spins up to a rotation period of a couple days, which is quite similar to what we measure for white dwarfs. So at least to first order, this model does a much better job of matching the data, although I think there are lots of little details of the data that are still hard to match with the model. So I don't think we have a complete picture yet. But I think we're starting to maybe understand the basic physical mechanism. So getting near the end of the talk, so I want to make sure we get to the rotation rates of the cores of massive stars. So what you can also do is, if you think that this model is doing a pretty good job of modeling this process, you can put the same physics into a model of a massive star, and you can calculate the angular momentum in the core of the massive star. So that's what's shown in this plot. These are models of the core angular momentum per unit mass as a function of time. So if there is no angular momentum transport within the star, then basically all these lines would be straight lines up here. But what you see is that the core loses 90 or 99% of its angular momentum. The vast majority of its angular momentum is lost during this phase right here. And this is right after the main sequence of the star. What happens at that phase is that the star has exhausted all the hydrogen in its core, so the core contracts by a large degree before it begins helium burning. So the core contracts, it tries to spin up and rotate faster. At the same time, the envelope expands and tries to spin slower. So you have a lot of differential rotation, and that fuels torques that transport angular momentum from the core outwards. So the core loses almost all of its angular momentum during that phase, according to these models. And then it continues to lose a bit more as the core continues to contract. And by the end of its evolution here, about the end of oxygen burning, so about a year before the star actually dies, the amount of angular momentum in the core is very small. It's of order a few times 10 to the 13, which is less than 1 part in 100 of what it started out with up here. So that's very little angular momentum. You can translate that to a rotation period of the neutron star that you would form. So if you assume this core then collapses into a neutron star, you can predict what the rotation period of that neutron star would be. And we predict that these rotation periods are something like 1/10 of a second, or 100 milliseconds. And it turns out that's pretty close to what we see in a lot of young pulsars. So some of them are born a little faster, like the Crab pulsar, but many of them are born with rotation periods of order 100 milliseconds. So this appears to be at least roughly consistent with the data we see for pulsars. You can do the same models for stars that form black holes. So now I'm making the exact same plot, but I'm plotting the angular momentum in the helium core, which is mostly what collapses into the black hole. And again, the star loses most of its angular momentum after the main sequence, so it ends with very little angular momentum. I'll come back to these green and yellow lines. There are a few models that do conserve a lot of angular momentum. But the basic prediction of these models is that for most stars that form black holes, the spin, the dimensionless spin of the black hole, which is a number that can range from 0 to 1, where 1 is a maximally rotating black hole, we predict that most black holes are born with very small spins. In fact, the number we predict is of order 10 to the minus 2. If you had a star that evolved on its own just due to these processes. And you can compare that with LIGO data, and that's what's shown with these gray crosses. And the data for most systems, so we don't actually measure the spin of each black hole, we measure the chi-f, so it's basically the component of the spin of the two black holes that's aligned with the orbit. And the error bars are often pretty large, but what you can see is that most of these black hole mergers, they have a chi-f, or a spin that's quite small, right? These points are clustered around zero spin. We have very few spin measurements that are very large and very few that are small, that are negative. So this is consistent with most of these black holes actually being pretty slowly rotating when they merge, which is what we're predicting, at least to first order from this model. Now, there are some points that do appear to have high spins. So I think this is 170729, I think, if I remember the event number correctly. So there are a few events that do appear to have substantial spin. And we do have a few models like this green and yellow one that do predict large spin for the black hole. But both of these models involve tidal spin up in a binary system. So all of the merging black holes we see, it's two black holes. So they came from some sort of binary system, whether or not they came from a globular cluster or a star that just started out as a binary star in the field is still highly debated. But the point is, in many cases, you can probably have a binary star during the evolution of the progenitor stars. And the binary star is very compact, and so the stars get tidally spun up. And that basically injects new angular momentum into the core. Whereas all these black points down here, these are single star models where you don't have those tidal forces. So I think that the systems that are spun up to large spins come from two channels primarily. One is this green point, which corresponds to a case where the star is tidally spun up during the helium burning phase. This could be after a common envelope event, where the star is now a very compact binary. The helium core is now spun up tidally, and that increases the angular momentum content of the core. So that's what's shown by this green line. So you can see that the core loses its angular momentum, but then it regains it due to tidal spin up. The second possibility is this yellow line. This is a model of what's called homogeneous evolution. And in that case, you start with a massive binary that's two stars that are very close. And what happens in some of those models is that rotational mixing in the star actually causes the whole star to burn all of its hydrogen into helium. So the stars just sort of stay as compact stars, but now they turn into a compact binary helium star. And those, again, the tidal spin up of those stars keeps them rapidly rotating throughout most of their evolution. So again, you end up with a pretty rapidly rotating star and a rapidly rotating black hole at the end of the evolution. So I think both these channels probably contribute to some population, some subdominant population of more rapidly rotating black holes. So there's a lot more work that needs to be done along these lines, but I think we're maybe starting to understand the basic physics of what's setting these spins, which can then be used to learn about the stellar astrophysics of where these black hole mergers are coming from. So I'm really excited about doing more of that in the future. Yeah, so the last thing I want to say about that is that we see some high energy transient events like gamma ray bursts and superluminous supernovae that we think might be powered by either rapidly rotating and accreting black holes or rapidly rotating magnetars. I think that the way you form those events is potentially by one of these channels that I just discussed, that you have a massive binary that's very close, it's tidally spun up, and that provides enough angular momentum to give you a rapidly rotating black hole or magnetar when the star collapses. So I'm continuing to doing some work along those lines to predict which stars will actually form those rapidly rotating central engines of those very luminous transient events. So I will leave it there. Thank you everybody for listening, and I'm happy to take questions and have a discussion.
So I hope you can hear me.
Yes.
Yes, I had a few questions. So
okay.
This phenomenon of gravity waves, or resonance locking. So I wanted to know how this turns out in three body systems or n body systems. Can
Yeah,
we model it even approximately at least?
that's a great question. I have not tried to look into that yet. I think, very few people have even tried to work on this for binary systems, so that's what we've been focusing on, that simplest case. I think that it can still happen in multi-body systems so long as your orbital frequency is not being changed by the binary interactions very much. So as long as you say you have a hierarchical binary with one inner system and then one star that's further out, as long as this orbital frequency is not actually changing very much due to interactions with this third object, then I think the resonance locking process can still happen. But if you had, say, a tighter binary where you actually had large changes in orbital frequency or eccentricity, if you have Kozai cycles or anything like that, it's not clear whether or not resonance locking could occur. I think there's a good chance it would not be able to occur in those cases. And the reason is basically if the tidal forcing frequency is changing, that means you can't have a mode that stays on resonance because it would be in or out of resonance depending on the phase of that variation. But nobody's looked at that, so that's a good question. I think it's something that should be done in the future.
Okay. So the question is that from one of the viewers. So we given a system, we use perturbations to characterize the system, see how stable it is, and so on. So can we go the other way around? So something like use those perturbations to detect if there were any disturbances before or something like that.
So which types of, yeah, that's a great idea. I think it has been used. I'm not sure if this is exactly what you had in mind, but there are some pulsating stars where you can time the pulsations very accurately. So this is just like timing the pulses of, we're timing the oscillations of, say, a pulsating delta Scuti star. And by measuring their time of arrival, you can basically measure the barycentric motion of that star. And so you can look for companions that are causing the star to move toward or away from the observer. And so that can be used to look for companion stars or companion planets in the same way that pulsar timing is used. And they have found, Simon Murphy is the person who's done the most work on this. He has found either dozens or hundreds of companion stars using this technique. It's been very powerful. Almost all the time, those are either normal stars or white dwarf stars. Simon, I know, really wanted to find some planets or black holes this way. To my knowledge, he hasn't found any, probably just because black holes are very rare. So he just hasn't looked at enough systems to stumble across a black hole yet. And planets produce a much smaller signal. I think, unfortunately, the data is not good enough to detect a planetary mass signal. Maybe a brown dwarf. And maybe in some cases he could find a planet, but I'm not aware of any planets he's found, but I think he's found some brown dwarfs.
So I have one last question. So could you go to the slide with the rotational evolution if possible?
Sure.
Of the main sequence.
Okay. I think it's on my... Okay, so let's go back. So you want one of these plots? This one?
No, the rotational evolutions.
Which rotational evolution?
Just after the of the methods that you described, the Tayler, Dino, something similar.
Oh, okay. This one?
Yes, this one. So I wanted to know why the graph sort of like goes up and down when it reaches the clump core stage,
Yeah,
and also more importantly, like why the surface rotation period has spikes in it.
yeah,
It doesn't
but,
follow the other two
yeah,
graphs.
yeah. So that's a good question. Let's start with the surface period. That's the easiest to understand. So what's happening here is the star is expanding. It's going up the red giant branch. Because it's expanding, it has to be spinning slower and slower. Most of the moment of inertia is in the envelope of the star. So to first order, this surface rotation period is just conserving the angular momentum of the envelope. And as the star expands, that means the rotation period goes like 1 over r squared. So the rotation period goes like r squared. So the rotation period increases enormously from 10 days to 10 to the 4 days. So this is the tip of the red giant branch. Then what happens is the star ignites helium in its core, and it contracts to a radius of about 10 solar radii during the clump phase. So that's why the rotation period drops sharply here. It's because the star now contracts, and so it spins up. So this is helium burning. And then it expands into an asymptotic giant branch star, and so the same process repeats. So this is the tip of the asymptotic giant branch up here. And during that stage, the star loses its outer layers, and so the only thing that's left is the white dwarf. And the white dwarf, which was basically the original core of the star, is rotating much faster. So that's the surface rotation. The core is doing something slightly different. So in these models, initially the core and envelope are well coupled, such that they're rotating at the same rate. On the red giant branch, the core contracts fast enough that it sort of decouples from the surface, and so it is rotating much faster. So there are strong torques here, but not strong enough to keep it synchronized with the envelope. So the core actually contracts and spins up a bit here. Then what happens here, this is the helium flash. And I said that that makes the surface layers contract, but it turns out it makes the core expand because it goes from a degenerate core to a thermally supported core. So the core actually expands, and so the core spins down right here, moves to longer periods. So during this phase, there's only a small difference between the surface and core rotation period. And then this is the asymptotic giant branch. The process repeats. The envelope expands and spins down. The core contracts and spins up. And then they meet each other. Once you've lost the entire envelope, then basically the whole star is the core. Does that make sense?
Yes, sir. It makes much more sense.
Okay, yeah, it's very hard to interpret these plots unless you've seen them before. So, but yeah, it's a good question.
Thank you.
So the black line here is the previous models of the Tayler sporoid dynamo, which have a similar evolution, except they're typically about 10 or 30 times faster. So they miss all the data, even though they get kind of a similar type of evolution. They're too fast relative to the observations.
Sir, when the helium burning starts, why does the graph stay flat for such a long time?
Yeah, during this phase?
Yeah.
Yeah, so during this phase, the stellar structure is not evolving very much. You have stable helium burning core. The luminosity is almost constant. It's similar to the main sequence, right? The star just doesn't change very much during that time. And so that means these rotation periods remain almost constant. It turns out there's not enough angular momentum. You can see that there's some angular momentum coupling that causes these blue and red lines to converge towards each other, but it's not enough to make the star rigidly rotating. And then eventually the evolution becomes fast enough that these curves diverge from each other again. But the basic answer is the star is just not evolving very much. It's kind of like the main sequence, except it only lasts 100 million years instead of instead of several billion years.
So there was a question from a YouTube stream. So a person wanted to know, how are the heartbeat stars different from twin stars? So, and what exactly forms these gravity waves?
So I guess I'm not sure what you mean by twin stars. There are certainly binary stars where the two stars are almost identical. I guess you could call those a twin star. What's really distinct about the heartbeat stars is they are very eccentric and very short period systems. So they are the systems where the stars really get just a few stellar radii away from each other during their closest approach. And that means you get a lot of tidal distortion during that phase. So that's when you can really produce the forcing that makes the stars oscillate. And the gravity waves that you excite there, they're basically, you can think of every time the stars pass by each other, the star sort of gets punched by the tidal force. And so that excites a wave that propagates through the star. And it propagates back and forth within the star. And what that means is it forms a standing mode. And so that the star is still oscillating the next time the system comes back through periastron. And so it gets another punch. So this happens over and over and over. So you can think of that as basically a continuous forcing that's forcing some harmonic oscillator inside of the star. So it's the equations are the exact same as a forced harmonic oscillator, which I'm sure you've all done in your physics classes. And so if you have a mode that has a frequency that is resonant with the orbital frequency, then you'll get coherent forcing, and so you'll resonantly excite the oscillation to a large amplitude. I hope that answers the question, but please let me know if I should clarify anything.
Yes, I hope so. There was another question as well, sir. So, how exactly does the Earth and Moon or the Sun fit into this as well? So, like you discussed about Saturn system, can this apply to the solar system as a whole as well?
Yeah, that's a great question. I think it might apply to the Jupiter system and maybe to the Uranus and Neptune systems, but probably none of the others. So it's not going to work very well for the Earth because the Earth is a solid object. It's not a fluid. So you don't have the same kinds of oscillations that can be resonantly excited. And also in a solid object, those oscillations tend to damp out very quickly. So you can't have the same kind of resonantly forced fluid oscillation that you get in a fluid object. It could happen for a star like the Sun if you have a planet at a very short orbital period. So like I said, it can probably apply to some of the exoplanet systems we see. But I don't think it would happen in our solar system because Mercury is far too distant for this tidal interaction to be important. Mercury just wouldn't excite a large enough oscillation in the Sun for that to do anything, even if it was resonantly excited. It turns out that even the oscillations Mercury excites, even though they're very weak in the Sun, they would also be so low frequency that they would they basically just damp out. They wouldn't form standing oscillations. They'd just form damped waves that don't form oscillation modes. So you couldn't resonantly excite that. But in some exoplanet systems, I think this could be very important.
So, like, can this somehow play a role in exoplanet detection as well? Or do we assume that it has already been detected?
I suppose it might be able to. If you had a resonantly excited oscillation, you could look for those oscillations just like we do for heartbeat stars, and maybe you could infer the presence of a planet or star that's exciting the oscillation. I think in practice that's hard. I don't think we've ever discovered a companion by that method. But it might be possible you could do it. The problem is that usually these oscillations are pretty hard to detect. Even in the heartbeat stars, which have the largest oscillations, it's still only 1 part per thousand. So you really need Kepler data or test data or something like that to see these. But yeah, that's a good idea. People have found planets by the equilibrium tide. So if you just, rather than thinking about the gravity modes, if you just think about the fact that the star gets tidally distorted and then that tidal bulge rotates around with the planet, that produces some luminosity fluctuation that we can detect. So there are many candidates for stars with hot Jupiter planets where we see that effect, and we've inferred that the stars have planets that way. So I think Sarah Milholland and Greg Laughlin worked on that. But that's a slightly different effect than the resonantly excited oscillations I was discussing.
Okay. So this might require like some heavy instrumentation or something, or more precise instrumentation.
More precise or longer baseline. Yeah. But I think what I'm most excited about is not detecting planets this way. It's learning about planets and binary star systems using that data. Usually there's easier ways of detecting them, like transits or radial velocity measurements. But once you know it's there, and once you detect these oscillations, you can learn about the evolution of the system using those measurements. So that's what I'm most excited about.
Are there any other questions from anybody here on the YouTube stream, perhaps? If there are none, we can conclude this.
Okay. Well, thank you so much for staying up late. I appreciate all the good questions.
This is like a normal day for us. We end our day late, so it's okay. And anyway, anything for physics as well. We thank you as well for taking time out of your life as a busy schedule to give us this wonderful and very interesting lecture as well.
It was my pleasure.
Thank everybody who has come here as well. Thank you.
Okay, thank you. Bye, everybody.
Thank you.